Thank you, Roberto. This is really happy time for me to share my understanding of what is geospatial data and what is geospatial analytics, or AKA GIS. We all know that the current time is the era of fourth industrial revolution. So many new technology are almost sweeping us off our feet. But I would call your attention to the bottom here. Geolocation becomes ubiquitous, place and time, embedded in all the data that's generated by these high-tech uh, technology, gadgets, and devices. So we have, the satellites taking Earth observation imagery. We have all the smartphones, smart sensors, electronic devices constantly generating data, and that data has location and time embedded in them. So what do we do with this large amount of data, right? We want to use them intelligently to solve our problems. That brings us the very fundamental approach for geospatial analysis, what we call the GIS, Geographic Information Systems. Traditionally, people think about GIS as a smart interactive map, right? You can interact with it and find solutions and answers to your questions. But in order to be smart, it's powered by a set of tools and procedures behind. It's a language to perform the task of spatial analysis. And in order to do that, the data are usually organized in a database in some structured way. Now, that's the old concept, old being maybe half a century long, GIS. And it has been used for a broad range of application cases. If you look at the challenges of modern time, almost every problem we face, climate change, public health, crime, sustainable development, anything you think, it has a space component in there. Overcoming these challenges requires insight of complex system owners. So that's why GIS is so important, because it provides a framework for us to organize our knowledge geographically. And it reviews patterns, relationships, and processes, thus broaden our knowledge and deepen our understanding of our world and the phenomena on Earth. And it helps us communicate, conceptualize, represent, and communicate our ideas, reconstruct history, illustrate present, or plan for the future. So it's a very important tool. And that tool is not just to make pretty pictures. It, first of all, allows us to explore the data that we talked about earlier, right? Huge volumes of data that we're submerged under. And it allows us to explore it, making quantitative maps, perhaps, to review the patterns, joining different properties of the measurements on different locations and show their spatial relationship, right? And then query the data by location, right? Those are just exploring what's going on. And then you get into the right side of the slides, the analytical piece of it. You can identify the co-location of phenomena, the proximity of different things, the connectivity through networks, through complex relationships, and then probability of what might be happening at certain location at certain time, whether the density has a pattern, whether it's clustered or sparse, distributed, whether there's a hot spot or cold spot. And you can also predict what might be the value at non-measured locations. So all of that are spatial analysis. And you can see that the GIS, geospatial analysis, is much more than what a very popular and well-designed GIS, which is the Google Earth, can do. Google Earth, I would say it is GIS too. It's a very purposely designed, simple, and user-friendly GIS that is good for looking at the world and then routing trips, right? But GIS includes a lot more than a Google map can do. So over the times, in the past half a century, the GIS technology had evolved from mainframe computer, beefy workstations, desktop, mobile devices, server and client type of networks into the web um, and cloud computing, and much more complex than decades ago. So it's a continuing, rapidly evolving technology. And conducting that analysis is quite challenging. The researchers had revealed that a lot of the analytical procedures published in peer-reviewed journals are very hard to replicate. And it's for a reason, because the data sources are scattered and may not come with the tool. And by space and time data, it's inherently complex and large, big data that's hard to manipulate. Tools may need license and needs a different specific operating system, need a lot of computing power, and so on. And when it comes to methodology and application, because it's wide applicable nature of this analytical methodology or methodologies, I should say, people who needs it come with different backgrounds, different technical levels. It's very hard to communicate complex technical issues across the board with these adopters. So what we at the Center for Geographic Analysis at Harvard is charged with is to promote the spatial thinking, the adaptation of technology, and also advance the technology to make it more useful for different type of users. And a part of our project is this spatial data lab project that is charged to build a platform to make it easy to use. Therefore, we can serve data, tool, case study examples, and training curriculums effectively. And we choose KNIME as our partner, as our core technology, core piece of technology to build this lab, this virtual lab, because it's open source, because it's easy to adapt, flexible to insert snippets of code or turn our workflows into native node, make it available to a lot of users worldwide. And it's also because it enables replicable analytics so that people conduct research using this tool can easily share their procedures with others. Our envisioning, and this is already being implemented, workflow is that professionals, researchers, and students use the open source KNIME desktop platform to build their workflows, do their spatial analysis, package them in a workflow, and then push it up to the business hub, connect to cloud data sources, and make it available as a data app on a browser. Then the end users with any gadgets with a browser capability can run these workflows. They could adjust parameters, the data, or using their own resources or the business hub server resource to run these workflows in their own version, right? And then see the reports, the maps, the dashboards, the charts, and so on. This is an integrated solution for feeding data into the researcher's hand, support their analytics, and enable their teaching and learning, and also make the methodology reach the application users. We think this re-engineered our research life cycle, because in the past, if you want to study, you assemble data, you build your analytics, you conduct your research, and then you maybe publish it or teach it, and that's done. It's locked up, right? But now we publish this as a workflow on the Business Hub. Other people can come in the repository, find the most similar one to their new objectives, and then maybe add new data, change some variables, modify the workflow, and then compose new cases, right? And develop new courses. And then they feed back their enhanced workflow to the repository for others to jumpstart their study. And these products, when they execute the workflow, right, sometimes with minimum modification, they could see the results, and then based on the result, quickly go back and then revise their workflow. So this makes research easier, faster, broadly reachable to others to share, and make research replicable. This work is sponsored by many agencies and industry, and we built our geospatial analytical capabilities based on many open source projects. And we contributed the Geospatial Analytics extension back to KNIME, and hoping that it will reach more users, and together will enhance our analytical capabilities. So with that, I'll stop, and I'll be happy to answer any question you have. Thank you.
Thank you very much, Wendy. This was super insightful. And if you guys have questions for Wendy, don't worry. We'll bring them back at the end of today's webinar for the live Q&A. Thank you very much, Wendy. See you later. All right, so let's now go back to a more, let's say, hands-on approach, and let's have a look at a focus on the Geospatial Analytics extension for KNIME. So this extension was released with KNIME Analytics Platform 4.7. It is a community extension, and it was jointly developed by the Center for Geographic Analysis at Harvard and KNIME. This extension has 10 different categories. That includes more than 60 nodes. You can use these nodes, for example, to read and write geospatial files, such as shapefiles or GeoJSON, but also to perform spatial calculations or transformations, and certainly also to visualize your data on interactive maps. Like any other KNIME extension, you can find the extension on the KNIME Community Hub. Just type Geospatial. The extension will appear, and you can then just drag and drop it onto your KNIME Analytics platform and prompt the installation. Once the installation is completed in the node repository, you will see all the nodes and the categories of the Geospatial Analytics extension. In the slides, we also have included a link to a few examples of the example workflows that you can use to explore this extension further. But today, when we were preparing this webinar, we thought, how can we show what you can do with the Geospatial Analytics extension in a live and interactive example? So to do that, we decided to create a data app that includes some geospatial applications. If you're not familiar with the concept of a data app is a tool that can be given to the end user to consume interactively via, for example, some visualizations, your analysis, without being exposed to the complexity that these analyses entail. So in this case, for today's case, let's say we created a KNIME Data Connect data app. What is it about? So the first page of our data app describe what KNIME Data Connect are. Data Connects are events that are designed to bring KNIME and local communities across the world together. Because these are local events, they often also are conducted in the local languages. So after this little intro to the events, we thought that it would be nice to show how the evolution of this event was across 2022. In fact, we'll be running this event for all of last year. And so, what was the best way of doing this? We thought that visualizing these events on a map was the best way. In fact, using a map allows us to have an immediate general view of how many events and where those were hosted. As you can see in the GIF, we had events in the North America region, Brazil, but also India and Europe. We also decided to add color coding to our map so that we could visualize the cumulative event registrations from the countries that had less to country or regions that had more. And as you can see, for example, the North America region and the Germany, Austria, and Switzerland region were the regions that had the highest number of cumulative registrations. And this is easily explained by another layer of information that we decided to introduce. That is to say, the number of events that each region hosted. In fact, in North America and in Germany, Austria, and Switzerland, we hosted more events than in other countries. And this is signaled by those little dots that you see on top of each country. In other regions, for example, the UK, we only had one event. Then we also thought that it would be nice to thank the organizer that joined this event. Therefore, we included a little card, let's say, there are tiles that include the pictures, but also the LinkedIn, and also to put in a table the preview of their talks, so we can rewatch it anytime. And next, what does the future bring? So we thought, since we are going to run KNIME Data Connects also in 2023, at the beginning of this year, when we built this data app, we thought it would be nice to create a tool that the user can use to discover where the next Data Connect event is going to take place. This is just an example, so we decided to restrict it only for the North America region. So in this simple tool, the user selects the country, the US or Canada, enter a city, in this case Montreal in Quebec, and show on a map the list of events and the closest event, the closest city that will host the next Data Connect event. In this case was Boston, and we also provide this on a map so you can actually see, let's say, the input location, and at the bottom, let's say, planned event for 2023. Finally, the data app proposes a little form that a user can fill to propose new Data Connect events. Now, these geospatial applications have relied on several nodes of the Geospatial Analytics extension. We decided in this webinar to focus on just 5 of them to give you a little bit a better idea of how you could use them. So, geospatial analytics in KNIME relies mostly on 3 basic shapes, 3 basic geospatial shapes. Polygons, which enclose a city or a country within its geographical boundaries. And here you have a little example of the city of Cambridge in the US, in Massachusetts. We also have points, which indicate just the coordinate of a location without any information on the boundaries. And again, the example of Cambridge, just a little point indicating the city. And also line strings. Line strings are lines that connect coordinates of 2 points. And here on the slides, you see the road network of the city of Cambridge. Now, these geospatial shapes are stored in KNIME Analytics platform in a new data type. This data type is called the geometry type. So once we have defined and understood what are these geospatial shapes, how do we get them? So the extension provides you with a category called the open datasets that allows you to get those basic geospatial shapes. One node that we particularly liked and found useful for our applications was the OSM boundary map. This node relies on the OpenStreetMap, which is an open geographic database, to retrieve boundary information. It's very simple to configure. You only need to input a place, for example, a city, a country, or a village. And as an output, the node will return a geometry type column, including the polygon of your input location, and a few additional information, such as, for example, the full name of the input place. In this case, for example, It gives us information about the city, but also the county, the state, and also the whole country. But after we retrieved these basic geospatial shapes, usually it's the case that we want to do some spatial transformations. And the extension also provides a set of nodes to do that. We have, in fact, a spatial transformation category. One node that we think is especially interesting is the projection node. Usually when, or by default, coordinates in the geometry type column are expressed or stored in degrees. Think, for example, of the coordinate for latitude and longitude. They are expressed in degrees. It is, in many applications, however, recommendable to transform, let's say, these coordinates to a new coordinate reference system. So going, for example, from a reference system that uses degree as units of measurement to one that uses meters. And we can do that by inputting predefined EPSG codes. If this sounds a bit obscure to you now, I'm sure you will find it more, you'll find clearer in the next slide. Another node that we think is extremely useful, or that was extremely useful in our applications, was the geometry to point node. This node, what it does, it returns a point representing a specific geometry. And here in the node, we have two options. We can choose between centroids and representative points. The first are calculated depending on the shape of the polygon, whereas the seconds are calculated are fixed points and are granted to be within each polygon. Choosing one or the other depends really on the application and on the use case. But just to give you a little example, think, for example, of we want to retrieve the polygon for France. And after we retrieve the polygon for France, we want to identify a point. So France, because it has many overseas territories, it is a multi-polygon. And if we decide to use centroids, the central point will be located somewhere off the coast of Western Africa. Now, if we are interested in locating a point that is within continental France, then in this specific case, using the option of retrieving representative point would be recommended. Another category in the extension is the spatial manipulation one. Here, for example, imagine that, as you saw in the previous slides, whenever we retrieve a point using the OSM boundary map node, visualizing this point on a map, it's usually can be a little bit hard because this is just a point, right? It's just two coordinates, so it can be hard to distinguish, especially if it is compared to the size of a country. So to let's say solve this problem, we have used, and it's recommended to use, the buffer node. What this node does is transforms the point into a polygon and adds a little padding space around that point. And so in the node configuration, we specify the geometry type column, and we also need to define the buffer size. Now, remember what I said in the previous slide. Using the projection node to go from one reference system to another that uses, for example, meters as units of measurement can be especially useful. And this is because, for example, when we want to define the buffer size, it is much easier to think in meters than it is to think in degrees. And also, we want to give you a little visualization example. So in this visualization example, we created a buffer area around the point of Cambridge. And as you can see, whenever we use the distance in meters, which is the yellow circle, we obtain a very clear, let's say, shape. Whereas when we are using a reference system, a coordinate reference system that uses degrees as unit of measurement, we obtain a little oval shape, which is the green oval shape in this map. Finally, the last category of nodes that we want to introduce is the spatial visualization nodes. As I said at the beginning, we can also, of course, visualize our geospatial data on a map, and that's probably the most exciting part of the analysis usually. We use a lot the geospatial view node, which, as you may already guess by now, uses as an input a geometry type column. and where they can visualize both polygons but also point objects. And the node itself allows for a wide degree of customization. For example, you can configure the marker toolkit, the size, the color, also the map, the base map you choose, and also whether you want to add a legend or not. In this case, for example, we decided to visualize the polygon for Germany. And as a bonus node, we would also like to signal the Kepler-GL GeoView node. This node uses the framework of the Kepler-GL to create, for example, 3D visualizations. In the upper screenshot, for example, you see a 3D visualization or rendering of mountains. And in the lower one, we rendered in 3D a specific city. And I like to ask all of you to guess and type in the chat, which city do you think we are rendering in 3D? And now, we also prepared for this webinar a little live demo. In this live demo, we're going to visualize first a location with its point on a map. And second, we're going to visualize country population versus capital city population. For this, I would like to ask Lisa to please come back on stage and take it away. Thank you, Lisa.
All right, thanks, Roberto. So I have prepared a workflow here for you to demo a few of the nodes that Roberto just introduced to us. I have already executed all the nodes just to save some time here, and I am trying to be quick so that I can show you everything. So what I'm going to do in this demo is I will first show you a few ways how you can visualize a location on a map. There are different ways, and I show you a few of them. And later on, I will move on, or I've built the small workflow here, which replicates a more realistic use case. As Roberto said, I am going to show you how to plot different population metrics against each other. With that, I mean I'm going to plot population on country level and population on city level within the same geospatial view or within the same map. But let's start simple. So as a first example, I have prepared this very small table here. It contains some coordinates. It's actually the coordinates of Cambridge in Massachusetts, and it's just a latitude and a longitude value. I have inserted it using, or I've read it in using table creator node, but of course you can use any other reader node you want. So if you have a CSV file or an Excel file, of course that works the same way. So this is a very, very simple example. So I have those coordinates and I just send them to the lat/lon to geometry node here. And the configuration is quite simple. So I just basically have to tell the node which is the latitude, like which column contains the latitude value, which longitude value, and I can select or define a coordinate reference system here using this code. I'm not going into detail here right now, but this is a default value. If you insert a node, this is the default value, and this is what we want. So I just leave it as it is. And then when I plot this using the geospatial view node, I zoom out a little bit that you can see this a bit clearer. So what you can see now is this point value here. This here, the entire window you can see is the configuration window of the geospatial view node. And the most important thing and the crucial thing you need to have is this geometry column that Roberto was talking about earlier, this new type, so to say. So you need this to plot it. Without a geometry column, you won't be able to configure the node. And then you can, set some other options here. For example, you can choose columns for size or color. I am showing you an example later, but for now, I just also leave it as it is. Also, you can change your underlying base map. So currently, we have this CartoDB map chosen, but you can also, for example, use the OpenStreetMap. So far, that's it. this would be one example if you have coordinates. Now, a second scenario would be you don't have any coordinates. For whatever reason, you don't find them, you don't have them. So what you can do and what comes in handy is this OSM boundary map node here. So I just configured the node by inserting the name of Cambridge, the state name, Massachusetts, or the abbreviation, and the country. The more detailed you can be here, I think the better it is. Of course, you can also just type in a country and then it gets you the boundary of a country. For this example, I just use Cambridge. So this OSM boundary map node geocodes this string value here and retrieves a bunch of geospatial information. Let's have a look here at this. I'll just make this a bit bigger. So this is the table we get from the OSM boundary map node. Bunch of information we can ignore for now. What is important at the moment for us is this geometry column here. Now, this geometry column tells us two things. First of all, the object we're dealing with is a polygon. So not a point, not a line string, it's that polygon, also not a multi-polygon, just a polygon. And the other information we get from here is this EPSG code, which again is telling us something about the coordinate reference system used. Now, as I just said, the geometry column is all that we need to plot something in the geospatial view node. So opening the configuration window of the geospatial view node where I sent the data table to, you can now see the difference to just the plot before. So now our geometry column is a polygon, so it covers here all the area that belongs to the city of Cambridge. And before, just to say that again, we only had the point. Now, one thing I really like, and I just want to hint that, is in this OSM boundary map, or in the results table, we also get the coordinates of the place we were looking for. So in case you want to plot a point and you don't have the coordinates handy, then you can also just use this node and then extract the lat and long column from this data table here. So this would then basically be the same example as above. So I have I just filter my data table so that I only keep lat and long, the latitude and longitude columns. And then I again just use the lat longitude geometry node, and this would be how it looked like. So we have this additional geometry column when using this node. And now you can also see the difference again. This is a point now, and before it was a polygon. So just to show you again, on the map, this would look like this. So we just have one point object. Now, another thing that Roberto mentioned, another one of those handy nodes or basic nodes we used is this, I'll just make it a bit bigger, I'm sorry about that, is this geometry to point node. Now, if I show you the configuration window, it's what we saw in Roberto's slides already. The configuration is quite simple. We use this node to convert a geometry object to a point object. So in our case, we have this polygon of Cambridge, and we want to convert it to a point. There are those two methods, the centroid method and the representative point method. And I just want to quickly show you the difference between those two methods in a plot. So what I did in here is I inserted two nodes and I just used both methods. And I brought them back together with this concatenate node, because if we want to plot multiple geometry objects, then we need to have them in the same column. And that's why I used the concatenate node. So what we have here is 2 point objects, one using the representative point method and the other one using the centroid method. And now if we plot this, you can here see the difference. Make this a bit bigger. So we have our shape of Cambridge. I just inserted that for reference. Now we can see the blue greenish one is the point retrieved from centroid method. The yellow one is the point retrieved from the representative point method. So here it's just a small difference, but as Roberto mentioned, if there are multiple, if, for example, France, which consists of multiple polygons, which are quite far away from each other, with this centroid method, we might end up having a point somewhere in the middle of the Atlantic Ocean, whereas the representative point method ensures that the point we get is somewhere inside one of the polygons. So far, so good. That's about the basics. So keeping an eye on the time, I'm happy to move on to a bit of more sophisticated example here. So what I just showed you were some basic configurations of the nodes, and as you could see, configurations are relatively simple. I just want to move on to an example where I'm trying to plot different metrics in the same map. And as we might know from other plots, it's sometimes a bit difficult if we have different metrics of different granularities and want to plot them. So what I have here, just as the basic data I'm using, just that I show you, I have a list of countries. I have a list of their capitals, so for each country the capital, and then I have two population metrics. I have country population, and I have the population of the capital city. And in addition, what you can see, the last two columns, they are the coordinates for each capital city, which, yeah, this is just the data I'm dealing with. And yeah, I would now like to have a plot somehow that shows me how populated a country is in contrast to how populated each country's capital city is. And this is possible, but to do so, a few steps are required. First of all, we need to retrieve the geospatial information for the countries. This is happening here in the upper part of the workflow. And as a second step, we then concentrate on the cities and are trying to basically create the geospatial data for each city based on our coordinates we have. And in the last part, in the third step, we need to concatenate everything, bring everything into a correct shape and data table so that we can plot it properly. So I would suggest to start with the country layer. So just to pop up this data table again. So we only have the names of the countries, nothing else. No geospatial information yet, no data yet. So what we can do is to use this very handy OSN boundary map node again. And I have put this or included this into this loop here so that this loop basically goes row by row and takes each country and then gets the geospatial data for each of the country. So what you get from that is a table like this. Let's make this a bit bigger. It's a very similar table as I've shown to you in the first part of the demo. So the columns are basically the same, but you can see we have more rows now, and this is due to the fact that we have a row for each country. And that the geometry column here is important to us right now. The other information we don't care too much right now. So what I'm going to do is I filter my data so that only the geometry column is retained. And then I add back this information from my initial data table so that I end up with this data table here, where I just have the country's name, the country's population, and the geometry column, which I need to plot. And just to show you how this will look like, I'm going to open up this geospatial view node here. And now you can see all the different country shapes from my list. This also demonstrates the situation for France, for example, because this is quite zoomed out now, because here we have islands which belong to France, and here's France, the country in Europe. So this would basically demonstrate the fact when we have a multi-polygon for a country. Anyways, so yeah, I've plotted these boundaries of the countries. And what I also did, now coming back to those settings here in the geospatial view configuration window, is I set a marker color column. And this means that I define that my country population should define each country's color. And down here you see also a little legend. And based on this country population, the color is defined. And so you can see very clearly, that Germany is one of the most, or is the most populated country of those European countries up here, whereas like Iceland or Ireland are among the lower populated countries. So this is the color coding we added. Now this would be part one. Now coming to the capital city level. So just to recall what data I have available, and as I said, I have the capital city, and for each capital city I have the coordinates. So I can just simply use the launch to geometry node again. So it's exactly the same thing that I've shown before. And this then already produces me the nice geometry column containing point value or point objects for each capital city one. Now to view that quickly in a map, this would look like you can see here. Make this a little bit bigger. So the countries, the capitals, they are of course scattered all over the countries. What I did here is now, coming back to those settings we have here, is I set this time a marker size column. So before we defined the column which should define the color, and now we set this capital city population to define the size of each point object. That way we can see that, for example, London and Paris are among the most populated capital cities, whereas, for example, Dublin, or also I know in Switzerland, Bern is very, very little populated, so it's very, very small. You have to zoom in very, very much to actually see the point, because it's so small, because 200 people living there. So those, this would be the setting for the size column. And now we basically have both of our layers. We have the countries up here, we have the capitals down here. Now what I'm going to show you is I concatenated both tables so that I have this one geometry column, which contains all my country objects and all my capital city objects. Now the thing is, if I plot this, I unfortunately don't get what I wanted, because so I zoom in a little bit that you can see the difference. So what I now get is all the countries being the same color, and the capital cities actually representing not only the capital city size, so not only the population of the capital city, but also the color coding that was supposed to be here for the countries. This is due to the reason that those settings are only applied to the upper layer, so to say. So just coming back to this data table I just showed you, with upper layer, I mean, this is, or the upper, or the level of the layers is defined by how those are ordered, the rows are ordered in here. So our countries, they are lower level, and then on top of the countries, we have plotted the points. So, I mean, this is not quite what I want. So I just want to show you very quickly a workaround, or a alternative way how to plot the two matrices. So what we need to do is we need to create a buffer around all of our points individually. So this means that Roberto was introducing the buffer node to us earlier that basically draws, I say it very, very in a nutshell. So this buffer area or buffer node basically just draws a circle around our data or point object, so that each point in this polygon, in the circle, has the same distance to the centered point. Now, a few steps are required to do so. First, we need to change the projection. This is due to the fact that currently we have the EPSG 4326, this CRS, the coordinate reference system, which expresses distances in degrees. We don't want that. We want to have the distances in meters. So I changed this projection to a different code using the projection node. I then define a buffer distance. For that, I used the math formula node. And my idea was just a very simple approach that I decided to use the city population as the buffer distance. Now, we do have some cities where, like, for example, France or UK are quite big. So I think, if I recall, UK has around 9 million people living there. So, of course, 9 million meters would be a very, very big circle. So what I just do is I take a fraction of my capital city metric. And then I simply created a loop inside this component here where I, again, go row by row and create this buffer object, which is basically a polygon afterwards, create a polygon representing a different size for each of my cities. This is the table that comes out. So what I have is my point objects here. I had them before. I showed them to you before. And then we have another column, which is a geometry column, another geometry column with objects of the type polygon. And those polygons, they have a different size for each of the capital city based on these distances here. So those are meters. So for example, for Vienna, we have 19,000 meters of a polygon or of a buffer distance. But I think it's easier if I just show you on a map. I needed to do a little bit of reshaping and renaming so that I can eventually match or concatenate to two tables. And this is very similar to what we had before. We have a table with our countries and the countries' polygons or multi-polygons, and we have our cities, which are also polygons now. And how does this look in the end? To show you the final plot that comes out is now, if I zoom in a little bit, you see what happened. So we now have the countries colored by country population. So this is due to the country population marker column we defined here. And the cities, they are now defined by those polygons that represent the city size. So, and yeah, with that, I actually am at the end of this quick demo here, and I would now like to hand it back to Roberto. He will say some final things before we are then moving on to the Q&A.
Thank you very much, Lisa. This was super insightful. And okay, so we have a few points that we would like to mention as a summary before we move to the Q&A. So in this webinar, what we learned is that what geospatial data and GIS technology are. We also learned how the Center for Geographic Analysis at Harvard and KNIME have teamed up to create a dedicated extension. We also show you a few keynotes that we used in our geospatial applications. We also show you a little data app that, let's say, includes those nodes. And we provided a few technical, let's say, details about the extension, such as that it's available as of KNIME Analytics Platform 4.7, which was released in December 2022. It wraps technologies of GeoPanda, KPGL, and OSM. And the extension offers a wide range of nodes to calculate, manipulate, transform, convert, and visualize geospatial data. And with that, I would like to move to the Q&A session. And for that, we will also need Professor Dr. Guan back on stage. Thank you. Perfect. And all right, so we have a few questions. I will start with a question to Professor Dr. Guan. So with your team, you support the research of many faculties, right, at Harvard. Can you maybe give us a little or an example of a request that your team, let's say, had to satisfy that was exceptionally interesting or extravagant?
It's easy to come up with some cases. It would be hard for me to judge which one is the most interesting one. Most of them are very interesting because sometimes I wouldn't imagine that, geospatial analytics could be applied in, the application cases that the professors brought to us. One example I could say was a recently published article on Nature, talking about how the U.S. voters, right, 180 million voting citizens in the U.S., where they live, and their neighbors, surrounding voters near them, how they vote influence the individual's vote. So you can quickly imagine that the analysis involves computing the 1,000 closest voters to each citizen who is in the voting age, and their partisan categories, and how the distance would influence this person's idea, and also how the pattern is distributed through the country. Some are people who live in a mixed environment, Democrats and Republicans kind of live as neighbors. In other places, they're segregated. You see blue patches in the neighborhood, and then you see, a distance away, there's a red patch. It's a huge computational challenge, 180 million times 1,000.
Right, that's
distances.
a lot.
Yeah, and you have to compute that quickly. You don't have, in the traditional way, there are months and years that you wouldn't be able to finish that type of computation. But of course, with high performance computing clusters at Harvard's IT department provides, and then improved algorithm that our researchers developed, that we were able to complete this type of analysis in a matter of a couple of days. But still sometimes it's considered very fast in the traditional way. So that's one type of really cutting edge technology applied onto social science problems. Another one is our collaboration with MIT, where we are taking tweets, geo-tweets, and using the machine learning algorithm to give it a sentiment score on how each tweet express a good or a bad, positive or negative mood, and then search from that database keywords such as climate change, and see people's attitude change through time and through space towards climate change in their expressed emotion. So maybe I could quickly mention the map behind me here. That's an older application. This is mapping the fall of the Roman Empire. Historical study, that when you put everything that you already know from text on a map, where the Rudin-induced pandemics happen, where the Romans built their roads into peripheral territories, and you see a striking correlation between where the roads lead and where the pandemic spread in time and space. So anyway,
amazing.
Sorry, I could go on forever, but I don't want to take all your time.
Thank you very much, Dr. Guan. We have a few more questions. One question I can maybe answer. So the one question was, if the Geospatial Analytics extension is already available in KNIME 5.0. With the current version of the extension, this current version is only compatible with KNIME Analytics Platform 4.7 and 4. And the connected bug fix releases. But in a month, we're going to have also a new version of the extension that is going to be compatible with version 5. And it also includes some new features, such as, for example, geocoding and driving distance support. So if you are using 5.0 5.0, a little bit more waiting time, and then you can also use these nodes there. There were, I think, also some questions about whether the slides and the workflows and the recording will be available. This will be included in the follow-up, so check your emails after the webinar. And I have one question for Lisa. I think she's perfect for answering this question. Somebody asked where and if is it possible to configure flow variables in these in the new nodes, in the geospatial nodes. Where do they find the configuration?
So short answer, yes, it is possible to configure flow variables. And in the workflow I've demoed you, there were 2 applications actually where we used flow variables, and that was within the 2 loops I had. Now, the configuration is a bit different. So if you're used to the 4.7 in general, there usually you configure the flow variables inside the configuration window. Now, in the new version, or like not new version, sorry, but now in this extension, we implemented the way how we deal with flow variables in the 5.0 in the early release access. Early access release. And that way, you right-click your node, and then you have the option to configure your flow variables like that. So this tab you usually know from inside, which is located inside your configuration window, is not there anymore, but you do it now just by a right-click. I mean, if you create a meta node or a component, you also can do this if you know, with right-click and create meta node, or click create component, or yeah, you can also configure a node like that. So this time, just right-click and watch out the configure flow variables option, and then the window opens. That is should be similar as you already know it from 4.7.
Perfect, thanks. We have time for one last question. So somebody asked about whether they can find example workflows. We have created a dedicated space on the KNIME Community Hub, which is called Geospatial Analytics Examples. So please go there, and you can start right away by drag and dropping them onto your KNIME Analytics platform. It's almost 6 p.m. in Europe, and it's almost the time to wrap up the webinar. So I would like to take the chance to thank Lisa and Dr. Guan for being together with us today for their talks, and it was a pleasure to have you with us. And well, we have a few comments, the last comments. If you want to stay in touch with us, you have the chance to do so on social media. Here you have on screen our LinkedIn contact, our Twitter contact, but also you can reach out to us on the KNIME forum. And in the streaming platform, you can just simply click on the Contact Us icon if you want to write to us. With that, I would like to thank everybody for joining and attending today's webinar. And till next time, bye-bye.